Okay, before the break, we were starting to talk about some physics, just some key points, and got up to starting to talk about Newtonian mechanics. Newton's first law, a body in motion will stay in motion unless acted on by an outside force, or sometimes you'll hear it equivalently stated as rest instead. A body at rest will remain at rest unless acted on by an outside force. The original version written in Latin, it has the moving version, because there's also in a straight line. A body in motion will continue in a straight line unless acted on by an outside force. Law of inertia, but we're going to talk about inertia. Somebody already threw that in the chat room when I mentioned that. It basically boils down to cause and effect. Things don't happen on their own. For every cause has an effect, and every effect comes from some cause. The second law is more mathematical. In force, we get a force anytime we try to change the velocity of some object. Mass is the substance making up our universe, making up existence. And the stuff in our universe all has a position. If we go to change that position, that's a velocity. And when we try to change the speed at which something is moving in our universe, when we change that speed, that's the application of force. And that's what we want to think about when putting our games together. So when you think about things moving, all of our game engines also include really, really nice physics engines that have been building for many, many decades now. So they're very, very accurate. So you don't want to just think about the thing moving from this X position to the other X position. You want to, in order to make it seem real or add a touch of realism for the player, you want to think about what force would cause that thing to move from one spot to another. Which kind of leads us into Newton's third law. Or is this picture? Got another picture to draw based around Newton's third law. And that is every force has an equal and opposite force. Every applied force has an equal and opposite force. And I guess I'll start here with the word opposite. And that relates back to this little arrow I drew over the F here. A force is a vector, which means our components are separate, and positive and negative indicates direction, right? Sort of like on a map, the way we normally draw those with a north, east, south, and west. So if we were traveling at some velocity northeast, then our vector, both of them have positive components. But if we were traveling northwest, we have a negative X direction and a positive Y direction. So that's what's meant by opposite, the direction of the force. So if our force is applied that way, there's something pushing back in the negative direction, right? My chair here, when I go to push on the chair, I can feel it pushing back against my hand, right? When I push the paper, I feel a lot less because it takes a much smaller force to move that paper than it takes to move that chair. You can feel it more. And there's another little subtlety there that comes in with the naming. There's one force, something we always have is our acceleration of gravity. Gravity pulls us downward, and in an acceleration, gravity is always trying to cause a downward acceleration so that the further we fall, the faster we go. Okay? So when I hold this piece of chalk, it has a velocity of 0. So that's how we can tell that gravity must be an acceleration, because when I let go, it does fall. So it started at 0, so something changed the velocity. So gravity is an acceleration pulling downward. I'll just draw it as I'll draw it as first. So when we have a person, there's this downward force, which comes from our mass times the acceleration from gravity, which we usually refer to as weight, right? That's what we can measure. How much does the earth pull us down? And that's the number we like write on our paperwork when we go to the hospital. This is a good way to measure it while we're standing on Earth. And that would be different, say, on the moon. Actually, you can watch videos of that when the astronauts went to the moon in the late 60s and early 70s, and they weighed a whole lot less. So to get ready, they put on those big suits. I wrote some big boots there. Put on those big suits and jumped in a pool, so the buoyancy would kind of counter some of that, and effectively they would seem like they weighed less, like they would on the moon. But that was actually a problem, because that did affect the weight, which is only going downward. The weight going downward, split up amongst their feet, it did affect that. So when they moved, that was fine. But when they tried to move, like say horizontally, that is still a regular mass times acceleration. That has nothing to do with gravity. So in the pool, that was lightened just like their weight. But when they got to the moon, if you have a 200-pound backpack on and you turn like that, it's still moving 200 pounds, right? Or well, the mass equivalent, pounds is a weight. The English unit equivalent to kilograms is slugs. So I'll say that if you have a 100 kilogram backpack on, if you're standing on the moon, it's going to weigh less, but in order to move it, to take a step forward or to turn, it's still that same mass, and you're still turning at the same acceleration. That's why if you watch those videos, you'll see the astronauts kind of doing backflips and falling over constantly, because they missed that when they were training, and they still, so downward is what they trained for, but they didn't train for the horizontal one, because they still had the full inertia going those directions. I'll use that word again, so we're going to talk about that. That's a big deal for us in game development. We have that weight going down, but as we get pulled down into a surface, say the surface of the Earth, where I'm at here, the gravity is trying to accelerate my body downward, causing a force downward. So my body is putting a force down into the ground. If you pay attention to what you feel when you're standing on the ground, you don't feel your body pushing on the ground. You feel the ground pushing on your body. So along with every time we have weight, we have an equal and opposite force coming back, which is typically called the normal force. Our normal force comes back, and that's the one we actually feel, right? I don't feel the force I'm putting into it. What I feel is the equal and opposite force that's pushing back from it. So that's why we call that normal. And that one can cause us some problems in game dev. So I'm going to do a quick example here. It's okay if I erase this picture, that turned into a mess. That was supposed to be a simple, clear picture, and I've got arrows all over the place, and ended up drawing a spacesuit on my stick man because I got distracted there. But equal and opposite is the main thing. So when we're moving our characters based off forces applied, we might have a situation like this, of this great big ogre. But mass equals 3 to try to keep the numbers somewhat simple here. And then we have our character, maybe our character is a little elf or a dwarf, a whole lot smaller than an ogre. So I'll put dwarf. A lot smaller than an ogre, so it's going to have less mass. And well, like those names imply, that ogre is going to be charging at our character. What I put in here? Acceleration of 0.2. When I was writing the example, I put 0.2. He's going to accelerate 0.2 units in its acceleration. So he starts at 0 and gets faster and faster and faster, like charging at our character from a complete stop for 12 frames is the example I put in my notes to tie this stuff back into games. So that's going to create a force that this ogre is moving with. And when he encounters our character, so when this force actually comes out and hits our character, we can punch in the numbers. The force is the ogre's mass times its acceleration, which would be 30 times 0.2. So we get 6. I'm leaving off the units here because just kind of looking at the numbers real quick and seeing how these things apply. So when the ogre hits our character, this is the amount of force he hits with, which means our character is going to push back with the equal and opposite force. I'll just call it negative F. So the ogre is going in the positive direction, and then we have an equal and opposite force going backwards. And they're going to have different effects on our character, right? This force that's applied at the moment of collision and the backward force is going to have different effects. So on our ogre, he's going forward with a velocity of, well, the accelerated from stop 0.2 units faster every frame for 12 frames. So he's going to got a forward velocity of 2.4. Sorry, I was looking at that number when I wrote that. 12 frames times 0.2 means his velocity has gotten up to 2.4. And our dwarf was just standing there with a velocity of 0. So after this force is applied, there's that equal and opposite. So I'll write the velocity afterwards. I'll put a little apostrophe. That's one of our standard notations for when we change things. So first changing the velocity for afterwards, well, we were going 2.4 in the positive direction. So that's why it's plus 2.4. And we're going to add to that a force of, well, the ogre's mass is 3. So if we divide that off, we end up with an acceleration of 0.2 in the other direction. So a negative 0.2 times 3. Does everybody see where that's coming from? So the equal and opposite force. So a negative acceleration, which in particular, that negative acceleration, I'm going to erase that 3 there. That negative acceleration of 0.2 means we're going to slow down a little. We start slowing down. Not much. Our big heavy ogre had a lot of momentum going forward, right? That's another word we're going to talk about here shortly. But when that backward force is applied from running into the much smaller dwarf, he's going to slow down a little. But our Our dwarf, this force has, that should be a 0.6, not 6. The force of 0.6, and his mass is only 1. So that force is basically like an acceleration of 0.6, right? So his velocity afterwards is that initial velocity plus the 0.6 for the acceleration. So he's going to speed up a lot. The ogre slows down a little, and this one speeds up a lot. A lot. Just to try to tie that into some game examples, right? Y'all can probably picture that. We have a little bitty character, some great big monster comes charging at him. He's going to go off flying, like bouncing across the room because of how much that force applied. And that equal and opposite has much different effects on those their different size masses. So that's the sort of thing we have to worry about and keep in mind, and might have to punch in a few numbers if our game's doing a few things. 746. I'm starting to think, might not get all the way through these lecture notes I have. I guess I'll erase this. Is it okay if I erase this side of the board? That stuff's from before the break, so it's been up there for a moment. So when we start thinking about those forces, we have to worry about situations like this, because our game objects aren't all going to be the same size, so they really shouldn't have the same mass. I think everything we've done in class would probably left that mass value at 1, but when we start working with forces, we should probably adjust that somewhat accordingly. So the other thing is, what slows us down, right? I guess going back to Newton's first law, body in motion will stay in motion unless acted on by an outside force. So what is that outside force that we need that's going to slow us down when we start moving? I'm just going to draw this as a block. So we have a nice rectangular character sitting on a flat floor. Early stages of a game development, and we're working this stuff out. And when we start moving it, we do so by applying a force, which makes that start moving off in the positive direction. But by Newton's first law, it's going to keep doing that until something else acts on it. And the things we have acting on it are friction and air resistance. So friction's a big one we want to calculate. We just talked about how this box has some weight coming down based off its mass and its gravity. Its mass and the gravity pulling it down creates a weight, which means the floor is going to create a normal force equal and opposite to that. The floor pushing back on that instead of moving, because the floor is solid, it doesn't move. So one way to think about it is those two forces are trying to move those things closer and closer together, as close as they can get together. Sort of like a tight seal, just tightly pressed against each other, which means that that seal, how tightly those two forces cause the floor and the object to be pressed together, it creates a force between them that opposes this. So from that little seal in there, we get a backward force that opposes our movement and eventually brings us to a stop, which just from living, you all probably know that's going to be the force of friction. And to calculate that, our force of friction, I'll put a little subscript F on it, is usually written as mu times the normal force. Force of friction is mu times the normal force. It's a very common one and easy to remember because you can see it spells fun. Well, sort of. This looks like a U. It's mu, the Greek letter U. And what that is a property of the surface. Like mu is, it's actually called the coefficient of friction. Coefficient of friction, which it's a property of the material. Property of materials roughness, I'll put it that way. That's one I feel everybody's familiar with from just life, right? We know what friction is. And when we have really rough surfaces, like a log in a firewood pile is a really rough surface. If we rub something against that, there's going to be a lot of force pushing back. But if we took that log and grabbed some sanders and made it smooth and kept smoothing it more and more and more, and then threw some clear coat polyurethane or something nice and smooth on top of it, then we could slide things across it very easily, right? They're like plywood, like a plywood bar. Right? If it's just the plywood, it's that rough wood surface. So when we try to slide things across it, we get a lot of friction. But usually bars get waxed, so then things will slide a long, long ways because it's a really smooth surface as a byproduct of making them waterproof so things don't get spilled on the bar. But the smoother our surface is, the less friction we get. So we have a smaller little scale, little value here. So that's the equal and opposite of our weight. So we can always find weight because gravity is a constant. Like on Earth, it's 9.8 is what we usually use. There's lots and lots of digits. We can carry that on as far as meters per second. 16 feet per second, or 9.8 meters per second is our change in velocity. It's fairly constant on Earth. It dissipates the further away we get, but we have to get a long way, right? Out where satellites are in geosynchronous orbit, it's still like 80% of what it is at the surface. We have to get a long ways before it starts to cut down much, but it's fairly constant, so we can calculate that, and we'll know the mass. So then all we have to do is change the sign, and we can find that number when we're calculating it. And then this coefficient that multiplies by depends on the material. So in our game engines, that's just a value we plug in there. We'll have a little box where we plug in how fast gravity is, how much our mass is. And then when we put our stuff together, there's also a spot where we'll plug in the coefficient of friction to say how much friction there is. Or there might also be air resistance. I'll try to draw that really lightly here, because air is a substance, and that's a little harder to calculate. And most of our game engines simplify air resistance a little bit by just treating it as friction. They'll just treat air as internally in the background. They just simulate air resistance by using a particular friction from the air. So that's what's slowing us down. So that's a value you'll want to think. Those are three values you'll want to think about: the mass, the gravity that's set for your game, and then how much friction is applied on your surface, which probably should change surface to surface, right? if your character's in a winter scene, you don't want the ground to have the same friction as a sheet of ice that the character can walk across. So that's going to seem wrong to the player. It's going to be counter to their intuitions. So that's usually the force that slows us down. So when things like this happen, Newton's first law applies, and this thing that's sped up a lot is going to keep moving until friction comes back in. So just some things to keep in mind as we try to simulate realism in our games. Is it okay if I erase this half? One more thing about forces I want to talk about, and then a note, then something about, it'll show up a lot when we get to debugging. So this is what was thrown into the next thing is what was thrown into the chat room earlier when I mentioned Newton's first law, because it's fairly well known and referred to as the law of inertia. But what does inertia really mean? And oh wait, not inertia. Inertia is that tendency to keep moving. But inertia, the next thing I wanted to talk about is impulse, the effects of inertia. So what's that inertia really? I started to ask the wrong question there. Inertia is the tendency to keep moving. So unless we stop something that's moving in this direction, it's just going to keep moving in this direction. And that key point there, that, well, as it's phrased in Newton's law, acted on by an outside force would make that curve up and then move in a different direction. So that's the inertia, the keeping it going. But this right here, this outside force, that interacting with inertia, leads to a concept known as impulse. And this makes a big difference. This is one that will cause problems when you're programming your game to move by the interactions of force so that it seems real. Is the physics engine knows about inertia, so that's going to try to keep Newton's first law going. Everything has that tendency to keep doing what it was already doing. If it's stopped, it's going to try to stay stopped. If it's moving, it's going to try to keep moving. So when we go to interact with those, we get into impulse, which is force per time interval. I guess it might be useful to look at the units here. So I use the SI units, the System International. So force is mass times acceleration. So we have kilograms times meters per second, which we usually write as squared, make it look a little neater, for force. And if we divide off seconds, we lose that bottom per second. So we end up with the units of mass times the units of velocity, which is momentum. So if you have to go look stuff up for this, you might also see it written notationally. The standard notation is a change in momentum. I forgot my Greek letter there. So if you see change in momentum, which we're going to talk about momentum here in a second, but as far as that's an important thing when debugging. So you might see this notation, but what that refers to is impulse, which is force over a time interval. So this one's best explained through an example. So for example, let's say we have a 1,200 kilogram car. That's your average four-door sedan. If you're not used to metric units. Your Toyota Camry or Ford Fusion, your typical four-door sedan is about 1,200 kilograms. Let's say it's moving at 25 meters per second. which is about 55 miles per hour. To dive into American units that we know. So we're going about highway speeds, but the metric system, especially in physics, makes a big, big difference. Our old empirical units were thought about beforehand, and the laws of physics were being wrote down at the same time the metric system was coming together. So the System International makes a big difference in physics because they were developed at the same time. So our metric units go perfectly with our physics equations. That's why I keep using those. But we have a four-door sedan moving at 55 miles an hour down the interstate or something. So it's going to take a certain amount of force to stop it, right? So the car moves. Draw a little car here. Moving along at some speed. If we want that to stop, we need to apply an acceleration that goes from 25 meters per second down to 0 meters per second to this mass. So to stop this car takes a specific amount of force. But there's two very different ways we could stop that, right? The same car here, moving along at the same speed. It's going to take the same amount of force to stop it, but two ways we could apply that force is we could hit a brick wall. That'll apply enough force to stop that car, right? Probably total destroy the car. If we hit a solid wall of moving 55 miles per hour, that car is total. Another way we could apply that same amount of force is we could hit a row of bushes. We could run into a bunch of little shrubs. And hopefully from personal experience, everybody's seen enough to know that both of those would stop the car, right? Hit that big concrete barrier, a pylon on a bridge or something, that'll bring a car moving at interstate speeds to a stop. Or swerve off the road and hit somebody, a row of shrubbery lining somebody's yard. That'll bring the car to a stop. But there's a big difference in how that car stops, right? This car is totaled, it's on its way to the junkyard. But this one just scratched the paint a little. But in both cases, the car came to a stop, which means that, well, the force of 1,200 kilograms, and we have to change by -25. We have to change our velocity by -25, so that's our acceleration. But that time factor makes a big difference. And how to phrase it here? Yeah, both stop, and it's because of the impulse, the time interval over which we apply that force. Depends on whether we total the car or just scratch the paint a little and go back on the road and get back up to speed. That's the same, but when time comes into play, that makes a big difference. And people will know this. So I put a note here. This is very important to keep in mind because of your if your impulse gets off, if you're getting the wrong reactions, right? Like your graphics show the car hitting a row of shrubs and the car is getting destroyed, like you just hit a brick wall, the player's going to notice, or vice versa. If players in the car and runs full speed into a wall and keeps driving that car, the player's going to be like, yeah, that's not real. That would have just destroyed that car. Because we spend so much of our humans exist in time, right? So our intuitions include time. So our intuitions don't necessarily go to forces directly, but our intuitions go with impulse. So as you're thinking about these forces, keep in mind the time interval over which that force is applied makes a big difference, which leads into human intuition. And the players will notice that lack of realism immediately. So as we want to think about things moving, not by changing the position, but by applying forces, and not just forces, we want the impulse. We want to think about how the inertia changes. And so how that force is applied over time, because it makes a very big difference to how things interact. And humans will spot it quickly when, and if you're trying to simulate reality in your game, people will notice the impulse getting off much quicker than the direct forces. Like, yeah, that's not that wouldn't exactly happen. Think about the example of hitting a brick wall or a row of shrubs. They have to apply the same force since they'll stop the car, but they're very different. It's okay if I erase this side and get into the last little part. So force of friction, and most of our game engines, they kind of cheat a little by treating air resistance as friction as well. It makes the calculation a lot easier because the actual calculation for air resistance is really tricky, and it depends on shape and temperature and all sorts of stuff. But if we just treat it as a special version of friction, it's really easy to run in our code. So we're usually simulating reality. So we're creating the illusion of what's going on, not necessarily an exact simulation of the laws of physics. We just want it to look appropriate. So remember, as you move things by applying forces, to always keep time in mind, because that will mess up our intuitions will catch that. In an Armada world, you all know how it goes. If you're trying to make your game seem real and you get your impulse off and people pick up on that, they're going to jump online and start big long complaint threads on Reddit or something about how janky your game is because it failed to accurately simulate physics or something. Y'all know how people are. So that's a good way to help avoid that. The last little bit I want to talk about is something that it's very important in the laws of physics. Lots and lots of calculations about it if you go into physics classes, and however far you go in physics, it's one of your key concepts that you want to think about. And it does show up when we're debugging. So I wanted to at least throw a couple notes into because this is something, whenever your game starts acting wanky, this is probably what went wrong. And that's conservation. In particular, we have two major quantities that are conserved: conservation of energy and momentum. So momentum, I'll do that first. It's typically notated with a vector for P. I have no idea where the P came from. That's just the standard notation for it. So when you see, if you're looking up physics equations to try to help debug a game or put together a plan for a game, and you see a P, that's referring to momentum. That's the product of mass times velocity, which we just saw here. That's what we get if we take a force and divide off time. There's something going. We have something moving. Something, which is mass. We have some stuff in our universe. Yes, Yeah, comment in the chat room that I was a little bit late seeing about what people will do if they notice that your attempt to simulate physics gets off. And impulse is one of the first things that will trigger their interaction. So as you apply forces, always think about the time over which that force is applied. Inertia doesn't change instantaneously. That only happens in a calculus class. In the real world, inertia can only change over a time interval. So we have to keep that in mind because intuition will pick up on that. Momentum is another thing that intuitions will catch because we have something moving. Mass is the substance that makes up our universe. Velocity is a change in position. So basically, whenever we have something moving, there's some properties about it, things that human intuition knows about it. And it's a property of that. It's a property of something moving. It's kind of hard to put a good word on it, but people will recognize it, right? When things are moving, we know stuff's going to happen, right? If I throw this piece of chalk at the chalkboard, y'all knew that was going to make a sound, right? There's the bounce back. That's the equal and opposite force. But the motion and the acceleration or deceleration, negative acceleration, that applied another force to send it going in the other direction. We have something else there. There was sound. When I threw it, my hand didn't make any sound. There was no sound. Well, no sound we could detect as it moved through the air, but that sound seemed to appear out of nowhere. And if we had like a radar gun, you would also be able to see that the backward bounce was slower than it hit the board. So we didn't get everything back when it bounced back. And some of that's because some of that thing moving turned into sound. It became something else. In particular, energy was transformed. So your typical 2 semesters in physics would spend a lot of time talking about energy. So I need to do a quick intro here. So a good intro is think about work. So energy. A good way to introduce it is what we call work in physics. That is the actual physics term for it. Work is force applied over a distance. A little colon here. Force applied over a distance. Is a good way to start thinking about it. So our formula is work is going to be force times distance, which force is mass times acceleration. But acceleration is a change in velocity, right? So if that times distance again. So work is mad. That's a common way to remember that formula. Mass times acceleration times distance. And acceleration is a change in velocity. So in order to change velocity at the start of our time interval, maybe 1 second interval, at the start, we're moving at some speed. And at the end of that interval, we're moving at a different speed. So really, we want to think about that to break it down straightforward. We think about the average there. We take our initial velocity minus our final velocity, add them together and divide by 2 to get our average change in velocity. So our mass times I'm gonna write this a little bit different. Yeah, so it's So mass and then a change in velocity, if we think about the average one, is 1/2 our change in position over time, change in time. And I'm change the notation to just delta x instead of that s like I was writing earlier. Is, well, we're doing this for game development stuff, so we're going to be thinking about x coordinates. And then we have another change in distance, which is change in position. Oh, and that's an acceleration, so that's squared times that times that. So when I put that together, we have mass. I'm going to draw a little arrow up here where there's more room. So we have our mass times the acceleration, which is a change in distance. Yeah, when we average that, we get a change in distance over that time squared times another change in distance squared. So change in distance squared over change in time squared, that's a velocity squared. Then we have half of it because we took the average. So when we do work on something, like actually apply a force and keep applying that force over a distance, right? Moving the chair, there's a lot of friction on the floor, so I have to keep applying that force to keep it moving. Apply it instantly, it stops quick. But keep it moving, continually apply the force. And through our math, we get back to this formula. And this is how we usually write the energy involved in moving that thing, in particular kinetic energy. That's the one that's going to give us the most problem in the most problems in game development. There's also potential energy and a lot of other things that we're talking about with games. We're considering graphics that are moving, so we'll just look at kinetic energy. We use work to derive potential energy as well. We'll just look at kinetic energy, and these two things, you'll notice that looks a lot like that. Anybody that's had calculus will immediately notice a similarity there, which I'm not going to get into here. One of those things drilled in your head. Should be able to get to that very, very quickly. From there to there, anybody that's had a calculus 1 class. So they're related, but again, it's the property of something moving. So momentum and energy, when we have things moving, we have those, and they're conserved. And in particular, energy is, well, this started as the force it took to move something. And then it took to turn into something, sort of an explanation as what it took to move that thing. Or another version, something falling, right? If I let go of this, as it falls, there's an energy involved. Couldn't really hear it at that time, but what I was doing earlier with the board, as it moves, when it hit that, well, I guess we can see it from distance. I'm standing here by the computer. I throw this, so it's going to hit the board with some force. The equal and opposite force should move it backwards. So if it's the same force, it should make it all the way back to me, right? But it didn't come back very far at all. It's right here. I know you probably can't tell much from the video. It only came back this far and made a sound. So this property in particular, the energy, can transfer into other things. And these things are conserved, so they can really show up as unintended consequences when we go to debug our games, because we can't lose any of that energy. And what's more, the way the physics engines that we use in games are set up, If we want sound, we have to add that in separately, right? That's an entirely different thing. It's like, oh, there should be a sound here, so we add a sound effect. So our physics engine in the game, like, can't create that sound. It can't turn some of the movement into sound. So there's a little discrepancy there. And the things that in the real world, we wouldn't lose any of that energy. But in the simulated world that we're creating, there's extra energy that would have been lost to a sound in a collision, for one example. Because we cannot lose any energy. The energy we start with has to perfectly balance out with the energy we end with. I'm going to erase the impulse if that's okay. Erase this half of the board. There's a couple other things to write. So both of these things are conserved quantities, and this is one that these will show up a lot as problems when we start trying to actually apply physics in our game, because there's a lot of subtleties that'll happen that the physics engine might go ahead and do, or the physics engine might not have been able to set up to do, that will manifest themselves as extra energy or momentum in our game objects. So we have to watch out for that. So they're conserved quantities, which means they can't just change. So for example, collisions. So before our collision, like the one drew earlier, where an ogre charges across the screen and runs into a dwarf, and the ogre slows down a little bit from that, so he's going to keep charging, but that dwarf's going to fly off pretty quickly because of all the energy that happened, the momentum. So before we have, momentum with mass with little p for player, little subscript, or the ones at the top are math, but the ones at the bottom are just labels. So our player has some mass moving at some velocity, plus, I'll go back to that ogre example, the mass of the ogre, I'll use M for mob, whatever the mob in our game is charging at us, has some mass and some velocity. And then after the collision, well, those things just bumped into each other. So they didn't change the mass. The mass is still the same. The mass of the player hasn't changed. The mass of the mob hasn't changed. We're just adding together momentum, so we're still going to add together momentums afterwards, but our velocities will change a lot. I'll put a little asterisk. I would read that as V prime. So after the collision, the new velocity. And that's what was going on in that example earlier, right? Before the collision, the dwarf was standing still, and the ogre was charging at about full speed. And after the collision, the ogre slows down a little, and the player moves a lot. But when we run through that equation, we didn't gain or lose anything. We end with the same amount of momentum we started with. And when your game starts doing wonky things, think about that. Take all of your masses, figure out what your speeds are, multiply them together, and that's probably where the very strange stuff is happening from. Same thing with energy. Beforehand, I'll do the same thing here. Yeah, I'll use those same scripts. So it's moving with some energy, a kinetic energy. So 1/2 the mass of the player times the velocity of the player squared. Okay. Which in that earlier example, our dwarf was standing still, so his energy would be 0 at this point. Plus 1/2 the mass of the mob, or the ogre in that example, times his velocity, which he was charging at full speed and had already been accelerating for several frames, so had a good bit of speed. He had a good bit of kinetic energy, which will be squared. This kinetic energy adds up a lot because our velocity gets squared. And that can turn into a very big number very, very quickly. We end up with a lot of energy. Then afterwards, well, we still have kinetic energy. So the mass of our player hasn't changed because all that happened was something bumped into him. But the velocity of that player changed a lot. In that example earlier, anybody wrote that down, follow along in the notes, what numbers did I have there? The ogre was going enough to have accelerated to 2.4 or whatever our units were. So when his big mass, we take that as an energy, 2.4 times some distance, there's a lot of energy there going up against that player's 0. So it imparts a lot of energy onto that player and makes it start moving, which then has to come from that. So it's going to slow down that big ogre from that example to some new velocity. Not that example we looked at earlier is not enough to stop the big ogre that was running at full speed, but it'll slow him down a little bit. And our character, which was at a complete stop, gets sped up a lot from that collision. I had a note here with momentum. One way to think about that is we have an equivalent overall movement, but it's distributed differently. Same thing with energy. One may have, after the collision, one has more to do. One has energy that can be used to do more afterwards, like our player that was that earlier example, the dwarf that was stopped, has energy to move now. And the other one has less because it has to balance out. We can't just randomly create energy. So when things like that happens, especially in collisions, that first sentence I had, we have the same amount of movement. We can't get rid of the movement we have. All we can do is redistribute that movement, which if you think about that, you'll probably very quickly realize that we only have so many things actually moving in our game with which we can just redistribute that movement to. So it can cause some wanky things to happen. So keep these two formulas in mind. And obviously we could, as we have more and more things in our game that there's just more things to add up in our sum. Write a little script and run through a loop for however many things you have. Add up all the masses, all the velocities, because the game engine knows what they are. I'm not saying to do this by paper. When you put those echoes on the screen, grab everything's mass, grab everything's velocity, figure out what the momentum is and echo that back. And then after the collision, echo that back again, the debugging process, and then compare those numbers to figure out where how that extra energy is getting redistributed different than what you intended. Which momentum is a nice way to think about that, because we can just think of that as extra movement. Right? The collision happens, and then after the collision, we have too much movement. It's getting distributed wrong, so we have to track down that extra movement that comes from a conserved quantity, so we can't get rid of it. Physics engines typically account for conservation, and it can definitely produce undesirable effects in our games. So if your solution breaks the law, breaks conservation laws, we're right back to that thing that I dwelled on about impulse. It's going to mess with people's intuition, right? If I threw a piece of chalk at the board and it did not make noise and bounced all the way back to my hand, which is, if we only think about the forces, that's what should happen, right? I applied a force going that way, it hit the board, which applied an equal and opposite force, which should send it back to my hand. So without transferring that into sound, it would make it all the way back to my hand. But if that happened, you would y'all would call that a glitch in the matrix, right? It's like, wait, that doesn't follow the laws of physics. When that thing hit the board, it should have created a bunch of sound and then not moved as far afterwards. Our human intuition knows that, so your players will notice that. And just like is in the chat room, the last comment in the chat room there, they're going to jump on Discord and Reddit and post. They'll make a whole big video of you on YouTube about it. They'll make a 20-minute video where they just keep doing that thing, little scene from your game over and over again, talking about everything that's wrong with it, because their intuition knows about conservation of mass and energy, or conservation of energy and momentum. So even if they're not going to sit there and do the calculation, they will know something went wrong. So you want to watch for that, and it will cause wonky things to happen. So obviously we're just doing a sum here, a couple of sums. So I guess you could, if you wanted to, pull up paper and do it, but just when you go echo things back to the console to check what's wrong in your game, just throw in a loop to add up all those numbers and check your energy. Mass times velocity is momentum. 1/2 mass times velocity squared is your kinetic energy, is that extra movement that is getting redistributed incorrectly will cause wanky things to happen in your game. So that's a big one for debugging. But and we might have a lot of things in our game, but that just means we need a bigger loop to calculate all of them. More paper if you just like to work it on hand, but we're programmers, so we're going to use the technology. 8:32. So as you're probably aware, physics is usually at least 2 semesters. I think I started talking about that this evening. And not just 2 semesters, it's almost always a 4 or 5 credit hour class at school. So it's 8 to 10 credit hours at college to study this stuff. And we just went over it in a very, very short amount of time. Hit a few key points to think about. The main one is, in order to replicate physics, we're just doing a simulation or an illusion of the laws of physics. So the big way to get that is by thinking about Newtonian mechanics, and don't change your position, apply a force that would result in that change of position. And it will seem much more natural. And when you start doing that, your conservation laws can cause problems. And so that's sort of something that's going to show up a lot, something to check when debugging. But it will make a big difference in how the players respond to your game and how well it looks. Hopefully give you some points there, and just, some key terms. It's one of many things in this course, so we can't spend a lot of time talking about physics. So one of the many, many things that go together. So this, as you all have noticed, this course is just kind of pointing you in that direction. Game development takes a lot of time. We certainly don't have a lot of time in a classroom. And so we just kind of have to get a flavor of stuff, get the starting point in that direction. And hopefully now, as we approach the end of the semester, I still have things to talk about Monday. Don't worry, I'm going to talk till we run out of time here, because there's so much to try to fit into 8 weeks. Hopefully now you have a few of those starting points in that direction. You have a better idea of what it's going to take to put a game together once you have time to sit down and put one together. So that was what all I had for that this evening. Does anybody have any questions about those? The starting points on the laws of physics, some key terms. Those formulas show up a lot. Use accelerations. Remember impulse, because when we change inertia, everything has inertia. That's our cause and effect that we cannot manipulate. And when we change it, it only changes instantaneously in a math class. In the real world, there's time involved, which leads us to impulse, and human intuition will pick up on that quickly. And when you start doing this, the laws of conservation might give you some problems when debugging. So that's the formulas to check. hopefully that gets you a start. Any questions? Okay, so I know that was a lot of information, barely scratch. I mean, that we didn't even scratch the surface of physics. That was like saying physics is something that exists. So if you all have any questions, let me know. Otherwise, that was it for this evening. I'll see you on Monday and we'll kind of, talk about a few more things in the time we have, because we don't have much time in the classroom here. So I want to get you all a good foundation to get started on your game development pathways. Y'all have a great night. I will see you on Monday. Let me know if you have any questions.
All right, I'll see you, Chris.
I'll see you Friday, Chris.